The question is, how do you calculate deformation of an axially loaded 1D rod when you have variable strain? For completeness, let's start by answering the question of how do we end up having a variable strain? Let's make it clear what we mean by variable strain. So here when we say variable strain, we mean a strain that varies with distance. There are several reasons why one would end up having a strain that varies with distance. Let's consider one specific problem that leads to a variable strain. That is this problem right here. We have a one-dimensional rod of constant cross-section A0, and this is subjected to a uniformly distributed load along the length, and the intensity of the uniformly distributed load is omega naught. Omega naught, therefore, is the force per unit length. The initial length of the rod is L naught. Let's cut out a small differential element of length dx out here and complete the free body diagram for that. On this cross section right here, there's going to be a stress, right? Internal stress. Let's call that a sigma. And if I multiply that by the cross sectional area A0, I get the force, right? We'll take the tensile stress as positive. So I'm marking this as a tensile force. Over the surface of the differential element, we have a force due to this distributed load omega naught, right? The total force will be omega naught multiplied by the length, which is dx. So omega naught times dx is acting in that direction. Because of this force, the stress over here is not going to be same as sigma. It's going to be a little different. Calculus says it will be sigma plus d sigma. So if I take sigma plus d sigma, multiply that by the cross-sectional area, that's going to be the tensile force acting on the other side of the differential element. Now let's go ahead and use the equilibrium equation in the x direction to write down a force balance equation for the free body diagram. Here it is, and this simplifies to this, what we call the first order ordinary differential equation for the stress sigma. Now we bring in Hooke's law to relate the stress sigma to the strain epsilon. Sigma equals E, the Young's modulus, multiplied by the strain. Now we invoke the calculus definition of the strain, epsilon equal du over dx, where u is the displacement, right? Now I'm going to combine these three equations, starting with equation number 1. Since sigma is E multiplied by epsilon, the left side of equation number 1 becomes d times E times epsilon divided by dx. And since E is a constant, at least in this problem, we are assuming that E is a constant, right? So you can pull this out of the differential sign. So this then becomes E multiplied by d epsilon over dx, but epsilon from equation number 3 is du over dx, and therefore this quantity becomes E multiplied by d2u over dx squared. And now put the right side of equation 1 over here. So what we have is a second order ordinary differential equation for the displacement u. This second order differential equation can now be integrated in order to find the displacement and the strain along the way. But before we do that, let's simplify this a little bit. First, let me bring the Young's modulus to the right side. So d2u over dx squared is what we have on the left side. On the right side, we have minus omega naught divided by a naught times E. All three of these quantities, omega naught, a naught, and E, are independent of x, and therefore these are all constants, right? Now let's go ahead and give a new notation alpha for this. So this differential equation now becomes d2u over dx squared equals minus alpha, where alpha is given by this expression right here, which obviously is a constant, right? Now integrating equation 5, once with respect to x, we have this. du over dx is what we get once we integrate d2u over dx squared once, right? On the right side, alpha becomes alpha x, so we have a minus alpha times x term right there, plus you end up having what we call an integration constant. So let's call that a C1. First, we recognize that du over dx is actually the strain epsilon, right? All right. Now the integration constants such as C1 are to be found using what we call boundary conditions, suitable boundary conditions. And in this particular example, we note that end B, point B, is a free end of the beam, right? And therefore, there cannot be a strain at that point. So our boundary condition that we could use here would be at x equals L, epsilon, which is du over dx, is 0. Now substituting these in equation 6, this is what we get. We have 0 on the left side because du over dx is 0. On the right side, we have minus alpha times L naught because x is L naught plus C1, right? So that it leads to this expression for C1. C1 is alpha multiplied by L naught. Now putting this expression for C1 in equation 6, we have this, right? So we have an expression for the strain epsilon as a function of x. So what do we have? We have a variable strain. So you can say this is one situation where you end up having a variable strain. Other possibilities are that in some problems, your cross-section might be varying as a function of x. Like, for example, if you have some kind of conical shape for the beam, your cross-section is varying with x, right? And therefore, the cross-sectional area is going to be a function of x, and therefore, you're going to end up having a variable strain in that situation. Other possibilities are, although rare, your Young's modulus could vary as a function of x. Here, since we have been following this method of integration up to this point, I'm pretty sure you can almost see how the next step is going to pan out, which is finding the displacement, right? Well, you guessed it, we integrate this one more time. Du over dx becomes u, and on the right side we have alpha, which is a constant, so we'll keep it as is. And then inside the parenthesis, L naught becomes L naught times x, and x becomes x squared over 2, right? And we introduce one more integration constant. Let's call this as C2. Once again, C2 is to be found using a suitable boundary condition. In this case, you can easily see the boundary condition would be the displacement at this point, point A, is 0 because it's a fixed boundary, right? And therefore, the beam is not going anywhere at that point. U has to be equal to 0 at that point. So at x equals 0, U is 0. Substituting these into equation 8, we get a value of 0 for C2. Now putting that back in equation 8, we have this expression for the displacement U. If we have numerical values for these parameters, obviously we can go ahead and calculate the displacement at a given point on the beam, right? So let's go ahead and do that for a given set of numerical values. L naught is given as 2 meters. E, the Young's modulus, is 70 gigapascal. Diameter of the beam is 20 millimeters, and omega naught is 5 kilonewton per meter. Let's go ahead and calculate the displacement at the middle of the beam and also at the end of the beam, point B. It's convenient for us to first calculate the value for alpha. So you substitute numbers for these parameters in a consistent manner. And I get 0.227 times 10 to the minus 3 meter to the power of minus 1 for alpha. You want to keep track of the units so that when we calculate the displacement, we'll know the units for the displacement. So here are the details of my calculations for the displacement. At the midpoint, x is 1 meter. At the end, x is 2 meters, right? Now you simply substitute these numbers into equation number 9, and I get these values. I get a value of 0.341 times 10 to the minus 3 meters for the displacement of the midpoint. Since this number is so small, it'll be convenient for us to express this as a millimeter. So that'll be 0.341 millimeters. And at the end, we get 0.454 millimeters. To wrap this up, in problems like these, there are two key things to keep in mind. One, when we have a variable strain, we need to perform integration in order to get to the displacement from the strain. Two, we need to use suitable boundary conditions to evaluate the integration constants. Different problems will have different boundary conditions, and we ought to look for suitable ones to use in evaluating the integration constants.